Imagine holding a tiny glass vial of a life-saving cancer drug. It's, incredibly delicate, highly complex, and it costs an absolute fortune to produce. Now imagine you're the engineer tasked with figuring out how to manufacture thousands of gallons of this fragile medicine without ruining the biology inside.
Right, it's a completely different scale.
Exactly. I mean, it's one thing to make a few pristine drops in a laboratory, but scaling that up to a massive industrial level, that requires a completely different universe of problem solving. So today we'll explain the science behind exactly how that happens.
It's a massive challenge, honestly.
Welcome to this deep dive into product selection, design basis, and bioprocess route identification using SuperPro Designer simulation software. And just so you know, this is part one of a two-part deep dive.
Yeah, it's a fascinating journey to take with you all. Transforming a brilliant medical breakthrough into a physical manufacturing reality, it really requires translating living biology into strict engineering code.
And to help guide you through this translation, I'm joined by our resident expert. He is a chartered biologist of the UK Royal Society of Biology and a senior lecturer at Tun Hussein on University of Malaysia, or UTHM. His name is technologist Dr. Rama Yusvana.
Thank you.
The goal today is to keep things friendly, curious, and totally accessible. We're going to demystify the architectural blueprint behind the medicine you actually see on the pharmacy shelf.
I am thrilled to be here. There is this massive hidden architecture behind every commercial bioproduct. And exploring how we actually use software to design that architecture is incredibly rewarding.
Okay, let's unpack this starting point. In the world of bioprocess design, the moment you transition from just having a great idea to actually mapping out a real facility, think of it like building a custom house. Week one is when you're dreaming about the mansion, you want the big windows, the wraparound porch, the grand staircase. It's all about the general excitement.
The fun part.
Yeah, the fun part. But week two is when the architect sits you down and forces you to draw the actual blueprints. You have to decide where the load-bearing walls go, how the plumbing connects, and whether the foundation can actually support the weight.
That is a brilliant way to look at it. Week two is the critical bridge. It takes you from a marketable bioproduct idea to drawing a literal process flow sheet that a computer program, specifically SuperPro Designer, can actually understand.
Right.
In the industry, nobody boots up the simulation software and just, starts drawing equipment at random on the screen.
I imagine doing that just creates an incredibly expensive digital mess.
Oh, it creates a simulation that will instantly fail.
Wow.
Yeah. The software requires you to answer a set of highly strategic questions first, like what exact product are we making? Why is it worth making? Is it technically feasible to simulate? What specific biological system will produce it? And perhaps most importantly, what are the acceptable assumptions we can make at this conceptual stage?
Wait, I want to pull on that thread about assumptions. What happens if you skip the strategic step and just throw, vague estimates into the software?
The phrase we use is garbage in, garbage out.
Ah, right. Got it.
Exactly. The assumptions you make at this conceptual design stage, they dictate the mechanics of the entire model. If your inputs are vague, SuperPro Designer can't calculate the mass balances.
Because it doesn't have the data.
Right.
Yeah.
You won't know how much water you need, how long a fermentation cycle takes, or where your bottlenecks are. The flow sheet just becomes inconsistent, and the entire design collapses before you've even simulated a single drop of medicine.
So far, we've learned that before simulating a process, we need a highly specific strategic blueprint. So to feed the software the strict parameters it craves, we need a specific product to design around.
We do.
And for this deep dive, we are looking at the therapeutic monoclonal antibody. For everyone listening, we'll just call it a mAb for short from here on out.
Good idea.
Let's define what a mAb actually is. It's a highly specific therapeutic protein produced by cultured mammalian cells. And they're commonly used in cutting-edge treatments for cancer, autoimmune diseases, and other major biopharmaceutical applications.
Which means, in process design terms, these are not just simple chemical mixtures. You can't just mix powder A and liquid B in a vat.
Right.
They are high-value recombinant biomolecules. Producing them depends entirely on keeping living, breathing cells happy in a sterile environment, followed by, multiple rigorous purification stages.
Okay, but if they require such a fragile, complex environment to survive, why do the source materials list process simplicity as a reason to use mAbs as our teaching example. I have to push back on that. You just said they rely on living cells. How on earth can that be considered simple to simulate?
It sounds like a total contradiction, doesn't it?
It really does.
The biology itself is mind-bogglingly complex, but the process route required to manufacture them is remarkably structured. It breaks down into very clear, compartmentalized stages. You've got inoculum preparation, cell culture, primary recovery, and purification.
I think I see where you're going. It's less about the complexity of the product and more about the predictability of the factory floor.
Exactly. Think of it like a complex car engine.
Okay.
The engine itself is a marvel of complex engineering, right? But it's surprisingly easy for a mechanic to work on because the manufacturer grouped all the parts perfectly.
Oh, I get it. So like a modern smartphone factory, the microchips inside are incredibly complex, but the assembly line itself is highly modular. There's a room for the screen, a room for the battery, and a room for the casing.
You hit the nail on the head. That compartmentalization is what saves the simulation. Because the upstream cell growth and the downstream purification stages are so distinct, SuperPro Designer can easily represent them.
That makes a lot of sense.
Yeah, you can draw a clean digital box around the fermentation time, another around the separation steps, and the software can calculate the math for each stage independently. The industrial route is beautifully defined.
So far, we've established that monoclonal antibodies are the ideal teaching tool because their manufacturing process is beautifully structured. But here's where it gets really interesting.
Oh, yeah.
How do you actually tell the computer what to do? You can't just type "make a cancer drug" into the command prompt.
No, you definitely cannot.
If you look at the commercial statement for this project, it simply says, "produce a therapeutic monoclonal antibody." That is the language of business executives.
A statement like that is a goal, but it certainly isn't a mechanical plan. You can't simulate a business goal.
Right. Contrast that with the engineering design statement. To get the software to work, engineers have to translate that simple sentence into this massive directive.
Quite a mouthful.
It is. It reads, design a fed batch mammalian cell culture process with inoculum expansion, seed train, production bioreactor, clarification, capture chromatography, intermediate purification, viral safety operations, buffer exchange, and bulk storage, capable of producing about 48.6 kilograms of purified mAb per batch.
That is the sound of biology being translated into mathematics.
But let's not leave you listening, drowning in jargon. We need to unpack some of those terms. Capture chromatography. What exactly is that doing in our digital factory?
Think of capture chromatography as a highly sophisticated molecular sponge.
Okay.
When the cells finish making the drug, the medicine is floating in this massive soup of cellular waste, proteins, and leftover food. The chromatography step uses special resins that act like a magnet, selectively grabbing only the mAb molecules and letting all the garbage wash away.
Oh, wow. And what about buffer exchange and viral safety?
Buffer exchange is simply swapping out the liquid the drug is floating in for a new liquid that keeps the protein stable.
Got it.
And viral safety operations are exactly what they sound like. Strict filtration or chemical steps designed to destroy or remove any rogue viruses that might have infected the living mammalian cells during production.
So by spelling out every single one of those mechanical steps, the software finally understands the physical reality of what we're trying to achieve.
Exactly why that translation is vital. A computer doesn't know what a medicine is, but it absolutely understands operating modes, flow rates, and separation efficiencies. Without that hyper-specific engineering statement, there's no simulation.
So far, we've seen how a vague business goal must be translated into a highly specific engineering mission. Now that the software understands the mission, we have to lay down the absolute rules of the game.
Yes, the rules are crucial.
In the bioprocess industry, this set of boundaries is known as the design basis.
Right, the design basis acts as the foundational contract for the whole model. If the foundation is vague, the entire flow sheet becomes inconsistent and just collapses. It sets the scale, the time frames, and the material limits.
Let's look at the core parameters of this base case contract. The target is to produce 48.6 kilograms of purified product per single batch. The cycle time for one batch is 14 days. If the plant runs continuously, overlapping those cycles, it yields 21 batches a year. That totals roughly 1,021 kilograms of therapeutic medicine annually.
And SuperPro Designer uses those specific time frames to figure out equipment scheduling.
Like when to turn things on and off.
Exactly. If a batch takes 14 days, The software will tell you exactly when to start the second batch so that your purification equipment isn't just, sitting empty waiting for the bioreactor to finish.
The form of the final product in our simulation is also a crucial boundary. The output modeled here is a bulk liquid, which is stored in 50-liter disposable bags. It is crucially not final filled syringes.
Right, no syringes.
Why draw the line there?
Boundary setting is critical in simulation. It tells the engineer that the final fill and finish operations, the incredibly delicate process of putting the liquid into the tiny glass vials you see at the hospital, are completely outside the scope of this model. Okay, if we included that, the complexity of the software model would literally double. We are strictly modeling the creation of the bulk drug substance.
Then we have to look at the raw materials required to make that bulk substance. In traditional manufacturing, raw materials are things like steel, rubber, or plastic.
Sure.
But in biopharma, we're dealing with massive volumes of highly specialized liquids. You need expensive serum-free media to feed the cells. You need specialized chromatography buffers for that molecular sponge we talked about. And you need staggering amounts of WFI.
We should definitely clarify WFI for the listener.
Please do.
It stands for water for injection. This is not tap water.
Obviously not.
Right. It's ultra-pure, fiercely sterilized water used across almost every stage of biomanufacturing, from making the cell food to cleaning the stainless steel tanks.
The scale of that water usage blew my mind. To run this single base case simulation, the facility requires over 1 million kilograms of WFI per year.
It's massive.
And if you expand the facility to run multiple bioreactors at the same time, that water demand skyrockets to over 12 million kilograms annually.
And every single drop of that water has to be heated, purified, and transported through sterile pipes.
That sounds incredibly expensive.
Oh, it is. The energy cost and the logistical nightmare of moving 12 million kilograms of water is exactly the kind of bottleneck SuperPro Designer is built to identify.
When you realize the sheer scale of moving 12 million kilograms of sterile water just to keep a few tanks of cells alive, you really start to see how much incredible problem solving is left to do in this field.
Absolutely.
By the way, for those of you listening who actually want to be the ones solving these massive logistical puzzles, UTHM offers master and PhD research studies. You can actually work alongside our expert guest or his colleagues at UTHM on various bio-based projects tailored to your interests. It's a fantastic opportunity to get hands-on experience designing the future of biotechnology.
We always welcome curious minds. The industry desperately needs people who can look at a 12 million kilogram water requirement and figure out how to, engineer a more sustainable, efficient solution.
Okay, so far we've locked in our design basis, aiming for 48.6 kilograms of bulk therapeutic liquid per batch. The boundaries are drawn and our massive water requirements are noted.
The rules are set.
The rules are set. It's finally time to turn on the digital machines and look at the biological engine driving this whole process. The upstream cell culture.
This is where the living biology truly dictates the engineering parameters. Our biological system is an animal cell culture, and the main event happens inside a massive 15,000-liter production bioreactor.
15,000 liters. To put that in perspective, that's the size of a small swimming pool, completely filled with a warm broth of living, fragile cells producing our medicine.
Quite a visual.
It really is. But wait, I have to ask a question on behalf of the listener. Why can't we just dump a handful of cells directly into that 15,000-liter tank on day one? Why do the design blueprints show this incredibly long seed train where cells are moved from tiny flasks to bigger and bigger bags? It seems incredibly inefficient.
It's a great question, and it comes down to critical cell density.
Cell density.
Yeah. If you drop a small cluster of cells into a 15,000-liter ocean of liquid, they essentially get lonely and stall out. Mammalian cells rely on chemical signals from their neighbors to trigger growth.
Oh, wow. I didn't know that.
Yeah. If they are too spread out, those signals dilute into the broth, and the culture literally dies.
I see. So you have to step them up gradually to keep them crowded enough to communicate, but not so crowded that they starve.
Precisely the balance we strike. You start the inoculum in tiny 225 milliliter flasks. As they multiply and get crowded, you move them to larger 2.2-liter roller bottles, then to 100-liter bags, then a 1,200-liter seed bioreactor, and so on.
Until you finally have a massive enough army of cells to populate the 15,000-liter tank.
Right, and SuperPro has to model the time and material required for every single one of those stepping stones.
That is an incredible biological constraint driving a major engineering decision.
Yeah.
But looking at the main 15,000-liter tank, the documentation states that it operates in a fed batch mode.
Yes, fed batch.
Let's break that down. So what does this all mean? What does fed batch actually mean, and why go through the hassle of doing it? Why not just dump all the nutrient media into the tank at the very beginning, close the lid, and save everyone some time?
Again, we are at the mercy of cellular physiology. High concentrations of the nutrient media are actually toxic to the cells.
Really? Their own food is toxic?
Yes. If you put 100% of their food in the tank on day one, the osmotic pressure and the chemical environment become overwhelming and the cells will die.
Oh, I get it. Think of it like bringing home a new puppy. Or even a houseplant.
Right.
If you pour a month's worth of kibble and water into a giant trough on the first day and leave for a month, the dog will gorge itself, get sick, and ruin its environment. Or if you overwater a plant, it drowns. It needs a slow, steady, controlled supply of food to thrive.
That is exactly the mechanism at play. In our fed batch process, we start the bioreactor with only about 1/3 of the total media required at a relatively low safe concentration of 17 grams per liter.
And then as the cells grow and consume that initial food, the software models a continuous slow feed of nutrients over the course of the 12-day fermentation.
Exactly. We slowly pump in the remaining media, but this time at a much higher concentration of 156 grams per liter.
Okay.
Because we add it slowly, roughly 7.6 liters per hour, the cells consume the concentrated nutrients almost as fast as they arrive. The overall concentration in the tank never spikes high enough to harm the culture.
That is such a delicate biological dance happening inside a massive industrial machine, and the result of that 12-day fed batch fermentation.
Oh, very happy culture.
Yeah. The system achieves a product titer of 5 grams per liter, and titer just means the concentration of our actual medicine floating in the broth. So 5 grams per liter in a 15,000-liter tank translates to roughly 75.5 kilograms of raw product.
Which sounds like a fantastic yield. But if we look back at our design basis contract, what was our target?
The target was 48.6 kilograms of purified product.
Exactly. We have 75.5 kilograms of raw product in the bioreactor, but we only need 48.6 kilograms at the end. Why the massive discrepancy?
Well, because the software knows we're going to lose a ton of it during the downstream purification steps. You lose about 4% just spinning the solids out in the centrifuge. You lose another 10% in some of the chromatography sponge steps.
Right.
The overall downstream yield is only about 64%.
Which is a beautiful example of reverse engineering. SuperPro Designer calculates those inevitable downstream losses and tells the engineer, look, if you want 48 kilograms at the finish line, your biological engine has to overproduce and give me 75 kilograms at the starting line.
That makes perfect sense, and that perfectly sets the stage for where we are heading next. Let's do a quick wrap-up of part 1. We've journeyed from selecting a highly marketable bioproduct to translating that business idea into a strict engineering design statement.
We covered a lot of ground.
We really did. We established our boundaries and realized the staggering logistical reality of moving millions of kilograms of sterile water. And finally, we got our delicate mammalian cells growing happily in a massive fed batch bioreactor, slowly eating their nutrients and overproducing our raw medicine to account for future losses.
We've built the foundation and started the biological engine. But as we just hinted at, having a raw product floating in a dirty broth is, well, it's really only half the battle.
We have a lot of work left to do, which is why we'll see you in part 2, where this deep dive will explore the incredibly complex downstream processing. We have to figure out how to purify that massive 15,000-liter soup, separating our pristine medicine from the cellular waste.
The fun continues.
It does. We'll also tackle the true economic costs of making these drugs, breaking down exactly where the millions of dollars are actually spent.
The downstream purification and the economic analysis are where the engineering design truly gets put to the test.
I cannot wait to get into it. But to leave you with a lingering thought until next time, if just tweaking the feeding schedule of a microscopic cell by a few grams per liter can dictate the success or failure of a multi-million-dollar manufacturing plant, what other invisible biological quirks are quietly determining the price and availability of the medicines sitting in our cabinets right now? Think about that tiny vial next time you hold it. See you in part 2.